talk is on interference alignment in cellular networks. So I'm just trying to present here vignettes of my work that we have been doing over the last 3-4 years. It touches upon at least 2 or 3 areas. So I hope there's something to take away for everyone here. So you have the wireless medium, and it's broadcast in nature. Everyone hears everything else, and there's going to be complex signal interactions in it. And we would like to know how many point-to-point links this network can simultaneously support. So you can think of it as decomposing this to multiple sets of point-to-point links, right? And the question is, how many point-to-point links can the network carry, right? And why are we interested in this question? Here is something by way of motivation. So I have here a 3-cell intersection, a 3-sector intersection with multiple antennas at both ends. And I assume that the base stations can sort of talk to each other, share some CSI, a few other metrics, but they don't share data. So it's not the network MIMO kind of a setup. And you could ask how many degrees of freedom does this network have? Or more specifically, what can you do if you restrict yourself to linear beamforming? And then you could ask how exactly can these beamformers be designed? And then at the end of the day, you want to know if these beamformers amount to anything at all. So in the broader framework of utility maximization, do these things have any role to play? Right? So that's where we are getting at. The network that I'll be focusing on is a GKMN network. So that's G cells. So cells are the triangles here. And I have K users in every cell. And I have M cross N antennas. So M antennas at the users and antennas at the base stations. Right? So GKMN keep appearing again and again. So you might just want to bookmark it. And I'm interested in degrees of freedom. Degrees of freedom is essentially the pre-log factor of capacity. It's the total number of interference-free dimensions one can create. And capacity at high SNR is simply log SNR times the number of degrees of freedom that the network can support. And of course, you can also give it a very formal definition. So the quantity of interest for this talk is what's known as symmetric degrees of freedom. So remember that we started off with a symmetric network. So the total degrees of freedom for this network is basically the degrees of freedom per user that can be achieved simultaneously. Right? So degree of freedom per user that I can support is my symmetric degrees of freedom, and that's my quantity of interest.
Right? Did you say what it means to be G interfering cells?
Oh, sorry. So I just meant to say that I have G base stations, and everyone hears everyone else. Everybody, it's a wireless medium, same spectrum, same frequency. So is it different than just saying, oh, I have G times N sort of antennas over there from some that are... I could define it as GN antennas, but here I assume that data corresponding to these 4 users is available only at this particular base station. With GN antennas, I would have to then specifically tell you which antennas have this particular user's data. So that's where you get into coordinated multi-point comp kind of a setup, right? So this is just coordination at CSI level, where you can sort of jointly design beamformers and power and things like that, but not data sharing. No, data is not being shared across base stations. Is that okay? Alright, so symmetric degree of freedom. The kind of channels that we assume are, so we assume a flat varying channel, time and frequency varying. Channel matrix is denoted as HAB, and importantly, we assume the channels to be generic. You can think of it as being drawn from a continuous distribution, What this basically ensures is that HAB has full rank, and that's something that we use in a lot of our proofs, right? And most importantly, I assume that the direct as well as the cross channels are known, have been measured, and that they are available at some centralized location. So the system model, HIJK is the channel from the jth user in itself to the kth base station. Each user is assumed to be transmitting D data streams, and the transmit and receive beamformers are denoted using V and U. So V is the transmit beamformer, U is the receive beamformer. So the signal model that emerges is something that I'm sure you have all seen before. So this is the received signal at the base station. So I want you to think of the signal model in the uplink. So this is the received signal at the base station, and then the base station projects it using the receive beamformer corresponding to that particular user. So that's, let's say it's UKL here. So it projects it, and then it tries to estimate what the transmit symbol was from this particular projected signal. One thing that I would like you to remember is this matrix Ri. So Ri is the collection of all interfering vectors at the ith base station, right? So if you were to go back to the picture that I had here, Ri would, for this particular R1, for this particular base station, would consist of signals coming in from all the 8 users here. Right? So it's just a collection. So it's the interference matrix.
So wait, you just said that's an uplink signal model?
Yeah.
But it seemed like before, a moment ago, your pictures like it had a certain, the arrows look like it's downlink model. Is that just the wrong picture?
This explains your question. So a lot of, pretty much all techniques here are linear. So pretty much anything that works in downlink also works in uplink, because once you decompose a network into its equivalent point-to-point links, you can use that point-to-point link. The direction of communication in that point-to-point link doesn't really matter. So I set up the signal model in uplink because it gives you some nice insights. But pretty much everything I'm going to talk about applies both ways. The degrees of freedom results are both for the uplink and downlink. The picture there was, yes, of course, for downlink. So, alright, so this is probably a very important slide here. There is this notion called spatial scale invariance. What it really asks is, how different is a G-cell K-user network with 3x4 antennas different from 6x8 or 30x40 antennas? So I'm just scaling up the number of antennas. And the conjecture is that if you are able to achieve D degrees of freedom per user in this particular network, then you'll be able to achieve 2D in that network and 10D in this network, right? That things are going to scale. Pretty much all degree of freedom results that we have now satisfy this invariance, right? This is so far a conjecture, and it was proposed by Sun and others in a few years back, right? So we don't yet have a proof, but this is something that we will use. So what this really does is that instead of me talking about degrees of freedom per user as a function of Mn, so the pair Mn for a fixed GMK, it lets me talk about degrees of freedom per user normalized over n as a function of the ratio m over n, right? So that's something I want you to get used to. So it's normalized degrees of freedom as a function of the ratio m over n, right? So because it comes in from spatial scale invariance, I append a small s here. So s d over s per user is what we will be talking about. Alright, so now I'm getting to the meat of the talk here. So we know from the very famous result by Kadambe and Jafar that in the SISO G user interference channel, you can achieve half degree of freedom per user. Right? The same result can also be applied to MIMO networks, except that it will require decomposition of the multi-antenna nodes into single antenna nodes, right? So once you decompose it, you then get a SISO network, and then you can go back and apply Kadambi and Jafar's asymptotic interference alignment scheme. And if you do that, what you can show is that you can show that certain number kmn by km plus n degrees of freedom per cell are achievable using decomposition followed by asymptotic interference alignment, right? So if you plot it as a function of this ratio gamma m over n, it looks something like this, right? That's all. Don't worry about the exact numbers here. If you don't like asymptotic interference alignment, then you will restrict yourself to interference alignment without symbol extensions. So what does interference alignment without symbol extensions mean? It basically means zeroing out interference from all the interferers at a particular node while making sure that you don't zero out signals, right? So these are the two conditions. So the first condition is to null all interference at a particular node, and the second condition is to make sure that you don't lose any of your signal dimensions in doing so, right? It so turns out that you really only need to focus on the first set of equations and not really on the second, basically because we assume channels to be generic, and because of that you can argue that the second condition is almost always satisfied and something that you don't really have to worry about. So if you were to just focus on the first set of equations, what you really have are second degree polynomial equations. So remember that u is a variable for you as well as v, right? So polynomial systems of equations are not as straightforward as linear systems, but there's one thing that you can always say. You can say that you must require more number of variables than there are equations, right? So if you were to sum all the variables in here and count the number of equations here, you end up with an equation of this form. That becomes a necessary condition for linear beamforming, right? So it says m plus n, total number of antennas must exceed gk plus 1 times t. Alright, so this is known to be a necessary condition. So if you take what you could achieve with asymptotic interference alignment and overlay this proper, so it's, sorry, I forgot to mention that it's known as the proper and improper condition. So a proper system is where you have more variables than equations, and if not, it's called improper, right? So if you were to overlay on that, you get a picture of this form, right? It still doesn't tell you much, but once we overlay a few outer bounds on this, it's a little more illuminating. So what I've plotted here are these plots for 2 cell 2 user, 2 cell 3 user, 2 cell 4 users per cell, and 2 cell. So this is in increasing order of network size. So 2 cell 2 user per cell is probably the simplest cellular network you could consider.
What's blue and what's red?
Blue was your what's achievable using asymptotic interference alignment, and red is the best you can achieve using traditional linear beamforming without symbol extensions.
It's an upper bound.
It's an upper bound on linear beamforming. It's an upper bound on.
So which one is applicable? M and N, right? Which one is applicable?
So V is always transmit beamformer on the user side. U is, or I should just say V on the user side, U on the base station side. So I just want to make sure when the signal is projected, all the interference terms get null.
And M is the number of.
M is the number of antennas at the user.
At the user.
N is the number of antennas at the base station.
All right. Now can you show the next one?
So this is as a ratio of number of antennas at user by base station. So I guess the plot of interest is really between 0 and 1. Right. So we are still trying to characterize the symmetric degrees of freedom, right? So we want to know what's the optimal curve here for all m and n, for all m over n. So notice that this plot applies to many cellular networks. That is, it's 2 cell, 2 user per cell, but I've not specified the exact number of antennas. So it's any line you draw, any vertical line you draw here corresponds to many cellular networks having the same ratio m over n. Right? So it's an aggregate plot actually. So then you come up with we come up with certain outer bounds on the degrees of freedom. These outer bounds are specified for certain ratios m over n. So I have a certain ratio, let's say p1 over q1, and it bounds the degrees of freedom that can be achieved when the ratio is less than that, less than p1 by q1, and another bound for right of p1 over q1. And we have these bounds for different ratios. They are a finite number. And so if I take all these bounds and I were to plot them, I can sort of already figure out what the optimal degrees of freedom look like. So you can see that it nicely bounces off. So these are the outer bounds, and it nicely bounces off between what you can achieve using asymptotic scheme and what you can achieve using linear beamforming scheme. But you see that as the network size grows, in fact it's somewhat clear from the next picture, you see that what you can achieve using this asymptotic scheme is much more than what you can achieve with linear beamforming schemes. And it appears that this is in fact optimal because the outer bounds tend to hug it very tight as the network size keeps growing. So there are results to say for some networks that this is indeed optimal, but there still are gaps in showing optimality. All right. So what this really shows is that you have 3 types of behavior here. One where the blue and the red do not intersect, one where they just touch each other, and finally where they intersect. So depending on whether they intersect or not, the DOF regions, the shape of the DOF is going to look a little different. So here it's all piecewise linear behavior. Here also it looks to be piecewise linear, while here there are 2 piecewise linear regions on the left and the right, and then there's something smooth going on in between. Okay. So if you were to focus on just the first 2 networks, you can show that this outer bound is indeed tight, right? That you can actually construct beamformers that match the outer bound. And you can also show the same for the second case, which is 2 cell 3 user case, right? The outer bound that we had previously is not tight enough, so we needed to tighten this particular bound here by a bit more. So how exactly do we go about designing beamformers that achieve the optimal DOF? So the construction is quite non-trivial. It's you need to really focus on how you choose your beamformers. But one notion that we found very useful was this notion called a packing ratio. So I'll briefly touch upon that in the next few slides. All right. So what really helped us was to look at interference alignment in a different light. Right. So what we originally had were these 2 conditions, and this set of equation was trying to null all interference there is. Right? But if you were to, for a moment, focus on this network here, which is a 3-user interference channel. So I have 3 transmitters, 3 receivers here, and I have 3 antennas here, and I have 5 antennas here, and I'm trying to support 2 streams for every transmit-receive pair. If I were to align interference in such a network, it should so happen that the 2-dimensional stream coming in from here and the 2-dimensional stream coming in from here, which are both interference, must lie within a 3-dimensional space at this particular receiver. This leaves 2 dimensions for receiving the signal at this particular receiver, right? So all interference alignment is trying to do is to design the beamformers so that the rank of Ri was your set of interference vectors, right? The rank of Ri is less than or equal to that quantity n minus kd. So if you remove kd is what you need to support signaling vectors. So all of your interference must be contained within a certain number of dimensions. Right? So that's what interference alignment is trying to do. It's trying to pack interference into a smaller dimension. Right? So that's where the notion of packing ratio comes in. So here I have been able to pack 4 interfering streams into 3. So I got a packing ratio of 4:3. So the way you go about figuring out how well you can pack requires you to understand how subspaces overlap with each other. So in this case, suppose I have two users with M antennas each, and I had N antennas here. They see a space of size 2m minus n that's common to both of these receivers. So there is a way for them to transmit such that this base station sees those transmissions as a single transmission. I could go further. There could be more overlap between what was common to these 2 users and what this particular user can access. So then I get the overlap between this 2m minus n space and this m dimensional space. Right? So in that case, I get a packing ratio of 3:1 because I've made these 3 transmitters appear as a single transmitter at this particular interfering base station. Right? So essentially, it boils down to a counting argument on how much of overlap there exists for any given m and n for a particular network. Right? So as an example, if you had 12 antennas at the transmitter and 9 at the receiver, then because you have a certain condition 3m minus 2n to be greater than 0, you know that 3 interfering vectors can be aligned into a single dimension. So that means that so I had 3 signaling dimensions for this particular base station from these 3 users, but they appeared as a single dimension here. This base station did the same. So 3 signaling dimensions and 1 interfering dimension. And if you continue this further, you are able to fill all the space with either signals or interference. And it so turns out that this particular strategy is indeed optimal. Right? So pretty much, so achievability pretty much requires you to understand how subspaces overlap and how much you can exploit this overlap. It's good, it works well for small networks, but extending this to large general networks is pretty hard because studying overlap of subspaces between like 10 users is very hard. Right? So this is a clear limitation, and we tried hard, but we couldn't really take it further by too much. So that's when we stepped in and we decided to do something very different. And the result of that is what you see in this plot here. So this is a plot for the 2-cell 4-user case. And what you see here is this beautiful piecewise linear boundary emerging, which turns out to be optimal on the left side as well as on the right side. And how we go about establishing achievability is actually very different. So previously we were looking at how exactly to exploit these subspace overlaps, but now we are going to say that we don't care about them at all. So we know that rank of Ri needs to be restricted, which means the column vectors of Ri need to satisfy a certain number of linear equations between them. Right? So one such linear equation is represented here, where these alphas are coefficients for that linear equation. So if you can satisfy this set of linear equations, you pretty much have achieved interference alignment. But remember that alpha is not known beforehand. Right? One option would be to set alphas to be completely random. Right? And you can afford to choose alphas to be random, provided the resulting linear system had more number of variables than equations. And it so turns out that if mv equal to 0 is the resulting linear system when you have chosen coefficients to be random, as long as, so this is basically checking for number of rows and number of columns, and as long as you can ensure variables exceed equations, you can reliably solve for aligned beamformers using this particular equation. However, there is just one little caveat that I haven't really touched upon, which is that this particular approach may not result in linearly independent set of beamformers for a given user. So if you want 3 beamformers for a particular user, this particular technique may not deliver 3 linearly independent beamformers. Right? To resolve that, what you really need to do is to run a quick polynomial identity test. Right? So I'm not going to go into those details, but that particular test is it's a one-time numerical test. Right? So if I have done it, no one else has to do it. The outcome will be the same. So what
these alphas are being chosen randomly?
Alphas are chosen completely randomly. So
and then they're also part of the CSI then, that's they're given. They're also shared among.
No, so I'm assuming that all of this design is happening at a centralized location.
Right, but then they're all just alphas are known at all locations.
Alphas can be just generated locally at this centralized location, and only the beamformers need to be transmitted.
Can you go back to the because maybe I'm confused. So you have 4 indices. Alphas have 5 indices, 4 indices, 5 indices.
Alphas have
P is an index or P is not an index. So there are 5 indices.
5 indices in all.
Right. So does base station L prime not equal to L need to know alpha L? Do all alphas need to be known at all the base stations?
So it depends. I mean, so I assume that all of this is happening at a centralized location.
Yeah, that's fine, but you also assume that all the channel information is known everywhere, right? So I'm not worried about. It's not like a complaint.
Alphas need not be known to any of the base stations. All they need to know is what the resulting V is.
All they need to be.
So alpha is just a parameter that comes in transients. So it plays a role in design, but there is no physical meaning attached to alpha. So because of that little technicality, it requires a numerical test to conclude whether this particular approach is successful or not. So that's the reason you saw that there were a lot of little markers here, and I did not draw something smooth because each marker there represents whether a particular test was successful or not, and the blue markers represent the numerical test being positive, and the red markers are where the numerical test failed. So it seems to delineate what's achievable and what's not. And there is another piece of work that came out simultaneously, and these boundaries match exactly with what was proposed. So we believe that this technique can indeed achieve the optimal degrees of freedom. All right. So if we were to put all of these things together, what we really studied was that we had now the colors have changed, so I apologize. We had the asymptotic line here, so that's the green curve there. That was what was achievable using asymptotic interference alignment. The black was your proper improper boundary. And the 2 piecewise linear regions that emerged were regions marked 1 and 3 here. So they are the most difficult to resolve. They are the regions where degrees of freedom is very difficult to resolve. And it turns out that degrees of freedom that are not on the optimal boundary, that are also below these 2 cyan lines, are very easy to achieve. So there is really nothing there. Degrees of freedom in region 2 can also be achieved using the unstructured approach that I just spoke about. Right? So this is all trivial. All of this is taken care by the unstructured approach. And that leaves us with this sliver here, where we know that this is an achievable region, but the design of linear beamformers for this particular region requires design of algorithms. So there is no closed form way of constructing these beamformers. Right? So that really motivates why we need algorithms for interference alignment. And it turns out that when the network size increases, this is the most dominant region. So algorithms do have a very significant.
In what sense?
In that this grows bigger and bigger and bigger. So this these two regions are very negligible in size, as in the number of degrees of freedom covered by this sliver is just grows bigger. So in this picture, I mean, this and these two ends are they shrink, and this region grows big as I, let's say, increase G or K. So this is what starts to dominate. So I'll briefly touch upon what we have been able to accomplish with regard to algorithms for interference alignment. It again stems from this alternate perspective on interference alignment. So what we really need is the interference vectors, the matrix consisting of them, to satisfy a certain rank constraint, while ensuring that the transmit beamformers have full rank D. It turns out that satisfying this particular condition is pretty straightforward. You just impose the row-reduced echelon form on V, so that basically you force the first half or first part of V to be identity and the rest to be random, left to design. So this is easily taken care of. So all you're looking for is a set of VI that satisfy this rank condition and this set of linear equations. Right? So it's natural to think of this as a feasibility problem. So minimize 1 subject to the set of linear conditions coming in from here, the rank condition on Ri, and the relations governing V and Ri. So you can think of it in this manner, but dealing with rank constraint dealing with rank in a constraint form is pretty hard. So what we do is that we push the rank to the objective, and we say minimize the rank of Ri. So now notice that there is no guarantee on what final rank of Ri what the final rank of Ri will be. Right? So we lose that guarantee here. But through certain algorithmic techniques, we have been able to ensure that the rank of Ri meets the necessary conditions. Right? So rank minimization problems are very, very well studied in the compressive sensing literature. Typically what's done is that rank is replaced with some kind of a surrogate function. Rank is a pretty nasty function to deal with, so you sort of smoothen it out with either the nuclear norm or the log determinant or something like that. And once you plug in this surrogate function, then you're into the familiar domain of convex optimization, and you can pull in tools from convex optimization to solve for the aligned beamformers. Here is just one particular result that we obtained. So this is for a 4-user interference channel with 2x3 antennas. We are expecting 1 degree of freedom per user to be achieved. And what we really see is that other techniques that are existing in literature sort of fall short of the number of degrees of freedom we require. But the algorithms that we devised, which are the ones here, are able to deliver on the number of degrees of freedom that we personally require. So that's a little bit on algorithmic effort. Finally, on what does all of this amount to with regard to system design, right? How are we going to use this? So remember that spatial resources could be used for one of 3 things. You could either use it to cancel interference from the interferers. You could do something like matched filtering to enhance your signal, or you could simply serve more number of users, which is basically multiplexing. The trade-off between multiplexing and enhancing signal is roughly what was captured by DMT theory, diversity multiplexing trade-off. Some insight on the trade-off between multiplexing and cancelling interference is given by interference alignment. So why do I say that? One key question that emerges in multi-antenna cellular networks is how many users one can schedule simultaneously on any given tone. Right? If you were to go with spatial multiplexing, you would simply say, why not schedule as many users as there are transmit antennas, right? K equal to n. But if you were to go with what interference alignment has to say, it says I can only align interference if k is less than or equal to a certain quantity. Right? So there seems to be this range for k that's not so easy to resolve. And further, because interference alignment is only focusing on cancelling interference, its significance with regard to network utility maximization, where you sort of need to strike the right balance between all these three objectives, is not very clear. So we set up a system level simulation to figure out what kind of a role interference alignment could play. So we again go back to the original three-sector intersection that we had, and our objective was to maximize the minimum rate, so that's maximum fairness that we wanted to achieve. The variables being transmit, receive beamformers and transmit powers. We assumed that CSI was shared but not data, and we assume one stream per scheduled user, and we assume a per base station power constraint. Right? And the optimization framework that we propose is that once you schedule a certain number of users in a cell, use interference alignment to only address interference from the dominant interferer. So if a user, in addition, if a user chooses to associate with a certain base station, also request that user to list out q other base stations around it that create significant interference. Right? So we collect the dominant interferers to the scheduled users and only address that interference using interference alignment. Right? So once those interferers have been taken care of, then we call in our utility maximization algorithms to then strike the right balance and to give us the final set of optimized power and beamformers. Right? For maximum fairness here, we used a bisection search that was proposed by Wiesel and others a few years back. Right? So that's the basic setting, and these are we sort of decided to use a realistic channel model. So we have path loss, shadowing, fading, everything taken into account, and a few other system parameters are in there. And these were the kind of results that we saw. So what you see here is the performance with and without interference alignment. So the markers with star indicate where interference alignment was not used. The square markers indicate interference alignment being used. And what we really see is that as the base station to base station distance, so as the network gets denser and denser, the number of users one should really schedule be equal to, in this case, 2, which is also the optimal degrees of freedom, which result in optimal degrees of freedom for the network, right? So this is the DOF optimal way of scheduling users. So you see that it's only when you do things right that the rates you can achieve keep growing, right? So, and then there is still some gain to be seen if you did not adhere to this particular rule. So in this case, we have violated it and then scheduled 3 users here. So we see some gain by cancelling interference from the dominant interferer, but not as much as we saw before. And when we schedule k equal to 4 users, there is really no role for interference alignment because alignment is not able to cancel interference from any of the base stations because there are just too many users to null out. So the key takeaways are that cancelling dominant interference helps, and as the network gets denser and denser, you must schedule fewer and fewer users until you hit the threshold imposed by interference alignment. Right?
So somehow things are getting better as the base stations get closer?
Yeah, that's because I consider an isolated cluster. So when I have k equal to 2, I'm able to address all interference. I'm able to null out interference from the other 2 base stations completely. So you would expect this to diverge. But if I were to pull in other interference, interference from other base stations. Let's say I considered a large 100 base station network, and I looked at this tiny 3-cell cluster in the center, and I shrunk the whole network, then of course it would saturate at some stage.
So it's getting better because the channels are getting better?
Yeah, it's just that very little path loss, signal strength is better. So I can support higher.
So somehow, did you sort of give a sense of how this model works with the distance? Like, as the distance in the base stations gets large, the distance from transmitters to receivers also gets large? Is that really what's happening?
So the way users are distributed uniformly in the 3 sectors. So when base stations are very close to each other, users are relatively close to their base station that's serving them. But they're also closer to the 2 interfering base stations. So if you don't cancel that interference, you're basically looking at the SINR, which would just be a few dBs. But the moment you remove those 2 interferers, you just get maybe 20, 25 dB. And you can only remove these 2 interferers completely if you restrict yourself to scheduling for the parameters that I've chosen, 2 users per cell. If you violate that, then it's not possible to completely cancel interference from these 2 base stations. So what this is saying is that as the network is getting denser and denser, this number k, which comes from M, N, and G, you should stick to that number. You should not schedule more number of users than.
So when you say no IA, so what exactly are these?
Yeah,
because the numbers are staggeringly high.
I just remove these 2 blocks. So I schedule and then I pass them on to the utility maximization.
Oh, so you're still doing some.
I still do this, but I don't address the dominant. So all of these algorithms are going to just converge to a locally optimal point, and they are myopic in nature. So they are not somehow going to jump to this location where all interference is null. It's basically to address that fact that that IA is really useful, interference alignment is useful, and you can null the dominant interferers and then proceed to the remaining part of the optimization. So the role is not that this can replace this. The role is it's basically that it can augment the performance, it can enhance the performance of utility maximization algorithms, provided it's used in the right setting and in the right way. So right setting being dense networks, and right way being making sure the K that you choose permits complete interference null. Right. That pretty much brings me to the end of the talk. So takeaways would be that linear beamforming can play a very important role in establishing, or does play an important role in establishing the degrees of freedom of MIMO networks. I just briefly touched upon 3 techniques that we proposed, and the complexity of each technique increases with the DOF demand. So the further away you are from the boundary, the easier it gets to achieve those degrees of freedom. And it can shed important light on interference management in dense cellular networks, and also some insight on how many users to schedule in dense networks. With that, I'll conclude.